Okay. Well, I guess good morning, everyone. Good to see everyone. Welcome to the Slice Architecture Seminar. It is our great honor to have Professor Onur Mutlu joining us. Onur doesn't really need any introduction, but many of us are very familiar with Onur and all the interesting work he has done in the past, and especially on memory system, and even actually the RowHammer. He actually one of the first folks actually discovered the RowHammer attack, and he has done a lot of really interesting work on memory system in general, and more recently on genomic acceleration, which is also equally interesting. Hopefully we have another venue to invite you back to share some of the genomic work. So we're very excited to have Onur joining us. He will give us some of his perspective of RowHammer after those few years, and also his vision moving forward for future memory system and hardware design. So with that, Onur, take it away.
Okay, thank you very much, Sophia, and thank you very much for inviting me. It's great to be here. I think last time I was here, maybe it was 10 years ago or so. And Krista was my host, and I was talking about memory-centric computing. Volleyball court still there? I don't remember, frankly. My memory is not that good. Maybe 8 years ago. Even that I don't remember. But I asked Sophia, what do you want me to talk about? And I offered RowHammer, memory-centric computing, and genomics acceleration. I think she left it up to me, so I picked RowHammer because I think there's some things to talk about here, but I'd be happy to come back and talk about other stuff also at some point. Like before I get started, how much time do we have?
15 minutes. We end at 12 noon.
And 12, okay. 45 minutes, hopefully. Okay, yeah, 15 minutes. I could do that 15 minutes also. I did that before, but so I have a lot of slides. Don't worry about it. I'll give you the gist depending on the time. So I have a kind of a reconfigurable talk. And feel free to stop me at any point if you have questions. We don't have to cover everything. So I titled this as kind of provocatively, can we be free of Bitflips soon? I don't think we'll be free of Bitflips ever. And it's going to get much worse, basically. I'll give you the answer to that. But I talk about RowHammer to freshmen. I teach the digital design and computer architecture class at ETH Zurich. Now it's 600 students or so. And I start with some future or ongoing topics. And I talk about RowHammer because I think it's fascinating. And I show this bridge. How many people know where this bridge is? Okay, you know, what is it? No, it's not Golden Gate. Yes, people mistake that. That's right. Given that you're here, you may think this is Golden Gate, but this bridge doesn't exist anymore. This is Tacoma Narrows, close to Seattle. And this is what happened to it, a bitflip, basically. And this is a good example of a bitflip from my perspective because it shows that it's a reliability problem, but it could be a security problem. It could be a safety problem as well. Essentially, it's a robustness problem. And you can read about this interesting bridge. I also use this example of these folks constructing New York on this rod, and they look very happy now, right? But if a bitflip happens on this rod, they will not be happy. So I'm going to talk about memory robustness in general. Security is a particular aspect of robustness, in my opinion. And I think even going forward, we need to think about robustness and security very generally. This is a very general thinking, in my opinion. Like if security is about preventing unforeseen consequences, and you may criticize saying that, oh, this is too general. But we're going to deal with this going into the future. We're going to design computing systems that are going to operate under many different conditions. In some conditions, we may not have tested the computers to operate in those conditions. If you go to space, for example, if you go to harsh environments. And I think we need to be thinking in this direction. Our computing systems, in my opinion, are not built with that yet. So this is an example of computing system that we're trying to build, right? This is Mr. Bean. He's already built this 20, 30 years ago. Of course, that's a different kind of system. So if he may not be very happy if he gets a bitflip over here. So clearly self-driving cars are what I'm alluding to here. So what is RowHammer? RowHammer is essentially the fact that you can induce a bitflip in commodity DRAM chips very predictably. And at the time we first tested this problem, we found out that more than 80% of the tested DRAM chips were vulnerable. Today, everything is vulnerable. We know that. But there are also solutions introduced, and we're going to talk about that. We're going to talk about the trade-offs of the solutions. And what's fascinating about RowHammer, to me especially, is that it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. If you find other examples, please let me know. I will correct that statement. And people are writing articles that look like this. Forget software. Now hackers are exploiting physics. It's actually interesting also, right? Okay, so let me give you a little bit background on how we stumbled on the problem. And we were working on memory a lot, and we were very interested in a lot of issues in memory, including performance, latency, bandwidth, etc. And we were invited to write this paper and give a talk at the International Memory Workshop in 2013. This kind of covers the perspective that I will also mention in this talk a lot. So I think memory scaling, technology scaling is not going well. And we need to scale memory in terms of technology as well as systems, right? Because we need a lot of memory, a lot of data needs to be processed. Unfortunately, we're having a lot of difficulties at many dimensions in terms of robustness, which is what this talk is going to be about, but in terms of performance also. And we've always argued that you need to have intelligent controllers to control the memory. Don't think about memory as something alone, but think about memory as part of the system and design the system together with the memory so that you can actually enhance the entire system as opposed to trying to enhance the memory system itself. And this is going to be the kind of takeaway from the talk. We need more of this thinking and more of the system design so that we can overcome memory's challenges. So now let's go to the low level. So we're going to talk specifically about main memory, and main memory today is overwhelmingly composed of DRAM, dynamic random access memory. And if you look at dynamic and random access memory, it has billions of things that look like this, virtually. Basically, you have this bit cell in DRAM. It stores charge in the capacitor, at the charge level of the capacitor. And you can access the capacitor using the word line, a bit line, and sense amplifiers. I hear some echo. Do you hear that also? Maybe. Okay, I'll try. not to speak here. Maybe it happens there. Basically, for DRAM to work, the storage unit, capacitor, should work, as well as the access unit, which consists of the sensing structures, should also work. Now, if you want to store more data, which is what we want to do going into the future, you need to reduce the size of all of these structures. As you reduce the size of all of these structures, reliability and noise become problems, and you get basically different types of errors. As I said, and this is the physical picture, basically. Physically, it doesn't look anything like this virtual picture, right? Today, people are actually doing a lot of interesting things to carve that capacitor so that it can store enough charge so that you can sense it. But even then, we're having problems. So we did a lot of studies about memory. This is one of the studies that we did that actually got us interested in a lot of reliability issues. This is a study that we did with Facebook. Essentially, we analyzed all of the memory errors that they have in all of their server fleet across the world in production data centers. And this is lots of memory errors. And we find, this is one example result we find is that the chip density, the DRAM chip density that you employ in the server correlates strongly with the failure rate that you get in the server. Basically, if the chip is denser, you get more memory errors. As a result, servers fail more. And if you're interested, the paper has a lot more detail on this and etc. So clearly, we're having effects, real effects of memory errors on real servers. In fact, big companies like this spend a lot of time to deal with these errors and correct these errors, etc. There's a lot of research, development, and money invested in trying to fix these errors. Okay, so we also did a lot of studies to understand these issues at a very low level. So these are FPGA-based infrastructures. This is an original version of it. We developed FPGAs where we could actually change the memory controller flexibly, such that we can do whatever we want to the memory chips, meaning send them commands freely of the program that's running in the CPU. So this is a soft memory controller, essentially. And we wanted to understand if, for example, if we turn off refresh, what happens, right? And this is one of the infrastructures, and we open source this infrastructure. It's called the SoftMC infrastructure, and people have been doing studies with it. More recently, last year, we updated it with the DRAM Bender infrastructure. Essentially, you can test DDR4 DRAM chips using these FPGAs. And we have a bunch of FPGAs we can support out of the box. If people are interested in working in this, actually, we'd be happy to support it. We've been supporting different groups, and they've been writing very interesting papers about this. Of course, the FPGAs you need to supply yourself. We don't provide those. But the software is all online, actually. So why did we build this? We really actually wanted to understand these scaling effects. And initially, one of the scaling effects that's really interesting in DRAM, I believe it's very interesting still right now, is data retention. So if you don't refresh DRAM, it loses data. Right now, my cell phone in my pocket is refreshing DRAM. It's in self-refresh mode, so it's wasting energy because of that. We wanted to understand this because as you reduce the size of the cell, this retention time becomes lower, so you need to refresh DRAM more. So if you bought DRAM 10 years ago, you needed to refresh it less, essentially. Today, the DRAM that is manufactured at the cutting edge, you need to refresh it more. And we wanted to get rid of that. We wanted to understand it. And there are many works that have shown that retention time profile of DRAM looks like this. At the time, you needed to refresh every cell every 64 milliseconds, but these works and also our work show that you actually don't need to refresh most of the cells as often. And we really wanted to understand how you can build a memory controller that can not refresh DRAM as often dynamically by understanding the properties of the cells. So this turns out to be not easy. I'm not going to talk about that, but it's fascinating. I think we should really look for getting rid of this refresh problem in DRAM because it's not good for energy, it's not good for performance. But I'm not going to talk about how we do that. You need to do a lot of online testing. You need to have essentially an intelligent memory controller because the retention time of a cell depends on the cell, depends on the values that are stored in the cell as well as cells around you, and depends on some quantum-like effects that you cannot easily predict. And that makes it really worse, actually. Again, this is kind of a teaser, if you will. It's a talk by itself, and we've written papers about it. And there are many more papers also that have been written that I'm not going to talk about right now. But that's one of the major reasons why we built this infrastructure, actually. But this infrastructure enabled us to do a lot of other testing. And what I'm going to talk about is RowHammer. Essentially, what is RowHammer? RowHammer is if you have DRAM, you have rows of DRAM cells. It's a subarray of DRAM. If you want to access a cell in one row, you need to activate that row. Apply high voltage to that word line. And if you want to access a cell in some other row after that, you need to deactivate this row. This is called pre-charge in DRAM. Apply low voltage to that word line, so you close it. Now, if you keep doing this repeatedly, activate pre-charge, activate pre-charge, activate pre-charge, or high voltage, low voltage, high voltage, low voltage, it turns out cells, some vulnerable cells and physically adjacent rows get corrupt, meaning they lose their charge. And this should not be happening clearly because what we're doing is we're just accessing this row. Nothing should be changing in memory because we're not even writing data into memory, let alone things that you're not touching. So these cells in these adjacent rows may belong to some other application, may belong to the operating system, may belong to something really important for security, right? And that's the problem essentially. We call this the hammered row, we call this the victim rows, and we show that more than 80% of the chips that we tested at the time were vulnerable. We're talking about 2012 right now. These are the initial tests we did in 2012. And the paper was written in 2014. Then this is a scaling problem because the chips that are tested, that were manufactured earlier, we could not induce errors in them. And we hypothesized that this is because cells are far away from each other and cells are larger. So the number of activations you need to do or the number of hammerings that you need to do to induce a bit flip is larger than the number of activations allowed within a refresh interval. So of course, if you actually are not able to do enough activations to cause a bit flip in adjacent cells and the cells get refreshed, the entire memory gets refreshed in the meantime, you can solve this problem, right? So refreshing the memory more frequently is a solution to this problem. But remember, we wanted to get rid of refreshes also. So this is going to be a challenge for us. So the modules that we tested that were manufactured between 2012 and 2013 were all vulnerable. So we said that basically this is a scaling problem and this is going to get worse in the future. So we need to develop solutions to it, and the solutions are not going to be easy, essentially. So why does this happen? I'm going to draw the abstraction level at the, let's say, I'm not going to go into the device level here, but if people are interested in device level physics of why this is happening, there actually works in that direction. Basically, DRAM cells are too close to each other and they're small. Access to one cell affects the value in nearby cells because of electrical interference between the cells and then between the wires and the cells. This is also called cell-to-cell coupling or interference. And my high-level example is when you activate one row, apply high voltage to one row, an adjacent row slightly gets activated as well. As a result, cells in that adjacent row lose a little bit of charge. And if you keep activating that row many times or hammering that row many times, charge in some vulnerable cells get drained if they're not refreshed before you lose the data. Right? Hopefully that makes sense. Right? At lower level, actually, it's a fascinating also. We don't exactly know how to model it at the device level, and there are papers about that, and I'm happy to talk about that separately. Now, this is very interesting. This is a very low-level bit flip, but it actually has enormous implications on the upper layers of the transformation hierarchy, because this bit flip is in your DRAM, and your DRAM is directly visible to your programming language, operating system, algorithm, everything up there. It doesn't have a controller that's protecting it as much. Storage, we actually have a lot of these bit flips. I'm going to talk about storage also, but storage is kind of protected, right? If a bit flip happens over there, there's a controller that's protecting everything else. But in DRAM, these bit flips can be immediately visible. Okay, so we also showed in that paper that a simple program, it's actually only a 6-line program, x86 program, you can actually get rid of the MFENCE over here, can induce many errors. Essentially, it's a user-level program that you run on your CPU. What it does is it selects addresses X and Y such that They map to the same bank, hopefully. It avoids cache hits. It avoids row buffer hits in DRAM. Row buffer is essentially a cache on the DRAM side. I'm not going to talk about that in detail. And it basically ping pongs activates, interleaves activates to X and Y, and hopefully you'll get Bitflips if the chip is vulnerable. Now, we also observed in the paper that if X and Y are selected carefully such that you have only one row sandwiched between them, the bitflip rate increases because now you're hammering one row from both sides. It's called double-sided RowHammer. And today's RowHammer attacks are all double-sided RowHammer attacks, actually. Okay, we basically showed that there are bitflips in real systems that you can induce using this user-level program. There's nothing special about Intel and AMD. Essentially, all memory controllers, all systems are vulnerable to this. Okay, when we wrote the paper, our first sentence was, memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on accesses or data stored in other addresses. And I still believe that. I think we should really maintain this property. Because otherwise we cannot really handle, because this leads to data corruption, right? And we said that if you actually take our program, someone can develop it to an attack that hijacks someone's computer or crashes someone's computer. Hijacking is, of course, very interesting. And we didn't do that in the paper, but these good folks from Google Project Zero read our paper. And about a year later, they published this blog post, which is a beautiful blog post, where they showed that they could actually take over a Linux kernel using RowHammer. This is a direct copy and paste from their blog post. I'll go through this relatively quickly. They also have a beautiful Black Hat presentation, Mark Seaborn and Thomas Dulien. But basically, they replicated the problem on their machines after reading the paper. They were able to induce bitflips in these machines, and they developed two attacks. One is escaping the Google native client sandbox, and the other is actually taking over the Linux kernel as root. I'll give you the basic idea. They have an interesting security attack, but again, I'm not going to go into the security attacks a lot in this talk. They were able to induce bitflips in the page table entries of this program, and these page table entries point to the page table of this program. So if you're able to induce the bitflips in the right bits, you can gain write access to your own page table. And if you gain write access to your own page table as a user level process, you can do anything to the machine, right? Because you can change your own permissions at that point. And that's essentially what they did. Now, this is easier said than done. If you're really interested in what they have done, they have an interesting page table spraying attack, which I'm not going to talk about. So people started talking about RowHammer, and they started drawing pictures like this. There's a lot of interesting jokes and pictures if you're interested. And one hacker on the internet, it's a famous hacker, said, RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. So I like this because it's actually getting to the core of the problem. So if you're stuck in this room, don't worry. Keep banging on the wall, and if RowHammer is in effect, maybe some door will magically open, right? That's a bitflip, essentially. Okay, so since we don't have a whole lot of time, I could talk about this for a day also. I will give you an overview of what has happened afterwards. Security folks actually picked this up. There are actually very interesting works that have been done. These are folks from TU Graz that show that you could actually induce RowHammer remotely using JavaScript and take over the machine of a website visitor. These folks from VU Amsterdam showed that you could, again, induce RowHammer in an Android phone and take over that phone. They actually did an application. I don't know if this app is already there in the Android store, but they were able to take advantage of the deterministic memory allocation patterns of the Android kernel to fool the kernel into allocating a page table entry of a user level program at a location that they figured out is RowHammer vulnerable. And then they were actually deterministically took over the machine. Again, this is a mouthful. I gave you the basic idea in one sentence, but these attacks actually are a bit sophisticated. They're not perfect. They're all probabilistic attacks in the end. Okay, people actually accelerated these attacks using GPUs. People were able to do these attacks on remote machines using remote direct memory access protocol in a data center, for example. These folks did essentially the same thing. These folks show that even if you may not be able to take over a machine, you could break confidentiality by accessing privileged data using RowHammer. Again, there's some sophistication over here that goes into it. You may think, oh, with bitflips, how do I access someone else's data? It's actually interesting because there's some data dependence of RowHammer bitflips that we're going to briefly talk about. And more recently, people have been also looking at neural networks, and they've been developing attacks that would greatly reduce the accuracy of otherwise, reasonably accurate neural network. And I think this becomes now even more interesting, especially if we start relying on these neural networks to make decisions for us in self-driving cars, for example. And industry has been developing attacks also. Google and Microsoft have been developing attacks. I'm going to talk about this a little bit later because it requires some a little bit more depth. But industry has also been developing attacks, which is the interesting thing. And they've been publishing in top conferences like Using Security and ISCA. So this may be another attack, or this may be a solution. So we've been writing a lot of papers about it. This is a survey. It's kind of outdated because we wrote it in 2019, but it covers a huge ground of work from the device level all the way to very high levels. More recently, we updated it, but this is also out of date right now because there's research going on. But if you want to get initiated in RowHammer, there are papers that are out there. So in this talk, I'm going to talk about basically switch between understanding RowHammer as well as solving RowHammer. I want to go into understanding RowHammer a little bit because solving requires understanding, and I'll keep switching between these two. But if there are any questions, I can take right now. I can take any time actually. Okay, one question in the back. Is it the same generation of DRAM operating at the same interface speed? So that's a very good question. No, there could be different interface speeds, but interface speed doesn't really affect RowHammer. It's really an internal problem. Yeah. Yeah, if you normalize for that, the generation, yeah, that's a very good question, basically. So what really matters over here is the row cycling latency, how fast you can activate, how fast you can issue the next activate. And that is almost constant across many generations of DRAM. In fact, this is one of the problems that we want to solve in DRAM also. This is really determining, for example, if you do random access to a bank, you're really limited by this row cycling latency. And if you can reduce this latency, that'd be great, but it has been almost constant for multiple decades in DRAM. Hopefully that answers your question. So it's really the size, what's really changing significantly is the size of the cell across those generations. So just to give you an idea, in most of those modules we tested, you could induce, I think, 1.4 million activations in a single row legally. And we would see RowHammer after, let's say, 100,000 or so activations at the time. Now that number has reduced significantly. Yes, I'm going to talk about that. Yes, there's whole spatial variation, and that understanding actually helps that. Yes. You see the changes in the core activation window for DRAM affecting RowHammer? Yeah, that's a good question. So that doesn't affect as much because that affects how much parallelism you exploit. And in RowHammer, as long as you activate one row a lot, you don't really need to rely on TFAW. So you don't need to violate TFAW. Although if TFAW is violated or if TFAW is extended, you could do RowHammer in many banks, right? Potentially. So you could induce more Bitflips. Okay, very good questions. So understanding RowHammer. So there's a lot that I can talk about over here. So these are the modules that we tested. This partially answers your question over here. So TRC is if you look over here, it's 48 or 49 or 50, basically. Not too much difference. Okay, I'm going to talk about three major things. One is, from the memory controller's perspective, what is the distance between these rows? So from a physical perspective, we hypothesize that these should be physically adjacent, rows that see Bitflips. But from the memory controller's perspective, we see a different picture. Most of the rows are adjacent to each other. Again, from these are addresses issued by the memory controller, but some of them are not adjacent. And one of the reasons for this is because internally, DRAM remaps the row addresses. And this is done for fault tolerance reasons, reliability reasons mainly. But this points out an issue. If you want to correct this problem from the memory controller perspective, you don't know which rows are physically adjacent. And if your solution requires that knowledge, then you may not completely correct the Bitflips. That's interesting. Inside the DRAM, you don't have this issue because DRAM manufacturer hopefully knows what kind of mapping they used. Okay, so access interval, how fast you can access DRAM, how fast you can issue consecutive activates. As I said, we were close to 48, 49, 50. If you reduce these are data from real chips. If you reduce the access interval, how fast you can activate, clearly Bitflips reduces, errors or Bitflips reduce. But in order to get rid of every single Bitflip, you need to reduce the back-to-back activation latency or increase the back-to-back activation latency to 500 nanoseconds. Clearly, this is not acceptable. You can throttle accesses, but if you throttle it non-intelligently, if you will, every access, you're reducing the DRAM performance significantly. We talk about refreshing. This is what DRAM chips used to be refreshed at the time, every 64 milliseconds. Every DRAM bank is refreshed. If you increase the refresh rate or reduce the refresh interval, you give the attacker less time to activate or hammer rows. So you can fit fewer number of hammers within a refresh interval. And at the time, we showed that if you want to get rid of every single bit flip we saw, you needed to increase the refresh rate by 7x. Clearly, that's not acceptable because we want to get rid of refreshes actually. So RowHammer and refresh actually are working against each other in a sense. Okay, so data pattern. I mentioned this in terms of refresh. So some data patterns are much worse. For example, with this data pattern, you get 10x errors because the coupling interference that you have between adjacent cells is much higher in this case, because this is partly due to charge coupling. And people actually exploit that in different attacks. I will not go into that. There are a bunch of other observations that I will not talk a lot about. Errors are repeatable is very important because if you can induce an error in a cell, you can predictably induce it again, meaning that you can profile the DRAM and figure out which cells are vulnerable and cause a security attack. ECC cannot protect these attacks, at least the way we do ECC today, because you get a lot of errors per cache line. And I talked about double-sided hammering that I'm not going to talk about. Okay, there's more in this paper, but I'm going to talk more about what has happened since since then. So RowHammer is actually getting much worse. We're going to cover some of these. It has many dimensions, and they're actually interesting things to study. I'm not talking about all these. HBM chips are as vulnerable, essentially. So if your machine learning infrastructure depends on HBM, hopefully you're not getting a lot of RowHammer errors over there. Now let me talk about solutions. We'll talk a little bit more about these understanding. So solution space is interesting. So once you discover something like this in the field, you need to clearly have some immediate solutions to protect the vulnerable chips in the field, right? Longer term solutions can be more sophisticated. And I'm going to argue for intelligent memory controllers here, which is already happening in industry, but we need more intelligence, I think, going forward. Let's talk about the immediate one. Immediate one has limited possibilities because we have very limited control on how we can change our memory controllers today, right? Memory controllers are not programmable today. You cannot run a program on your memory controller. Very limited control in the BIOS exists, so you can increase the refresh rate. I'm going to talk about that. This is a more detailed slide over here. So you can build more robust DRAM chips, put more isolation between cells, or use error correcting codes. I think these solutions are very expensive, used alone. We don't know how to do it, and DRAM manufacturers are actually doing a lot on this side. And some on the side, but error correcting codes actually are not a good solution, in my opinion, to this problem if they're used alone, because these errors, we know exactly why these errors are happening, right? You keep activating a row and you're getting an error. Error correcting codes are very good for errors where you don't know what's happening, right? Like if you have a soft error, a transient error, a particle hits, you get a bit flip. It's random, and error correcting codes are very good for that. Increasing the refresh rate, I don't think this is a good solution, but this is the immediate solution, as we will see. Physical isolation, isolating aggressor and victim rows at the software level or hardware level. Usually this is very expensive. So I think we're today left with these two solutions, but there's room for, I think, creativity over here. Reactive refresh means that you keep track of which rows are activated a lot using either probabilistic or deterministic mechanism. You can use access counters, or you can have a probabilistic mechanism, as we will see. And once you figure out a row is accessed a lot, refresh the victim rows or potential victim rows, physically adjacent rows. This is interesting, and there's a lot of papers that are written in this topic. Complexity is an issue over here. Proactive throttling says, figure out again which rows are activated a lot. Don't access them a lot, basically. Throttle access to them such that you don't induce bit flips. So I believe these are actually very interesting, and a combination of those could be interesting going into the future. So we're going to talk about some of these, but feel free to think about these because there are other solutions that may be present that is not covered over here. So in the end, I think there's a huge trade-off space in terms of cost, power, performance, and complexity, especially if you want to get rid of bit flips. So security, I'm not going to put in security in the trade-off space over here. You could also put that over there. You could tolerate some bit flip rate potentially, but that complicates the trade-off space. Okay. I think people may be developing solutions in the back of their heads right now, which is good. So, okay, how did industry actually react? Essentially, they increased their refresh rates because that's the only thing that they could do easily. And they could have a patch that would increase the refresh rate and the memory control. This is from Apple. Basically, they said they mitigated RowHammer by increasing the memory refresh rates. They didn't say by how much. probably by 2x. But as our data showed, 2x is not enough to get rid of all of the Bitflips. This reduces the vulnerability, but doesn't get rid of the vulnerability. And Apple is nice because they actually referenced our paper in their security release. It's good for companies to actually do that. Okay, so what was our solution that we suggested at the time? I think it's actually a nice solution, but I think it doesn't work alone today because RowHammer has become much worse. So our solution was basically very simple. We said when the memory controller closes the row, it should flip a coin and with very low probability activates adjacent rows. This requires the memory controller to know which rows are physically adjacent. So we're back to that observation that I mentioned. So this requires some changes to the memory controller to understand. So this gives you a very good reliability guarantee. And if you're paranoid, you can adjust the value of P, which is great. This is actually very low cost because it's stateless. You don't need to keep track of anything, right? Well, anything meaning access counters. There's no access counter associated with any row. And we showed that actually its performance overheads are negligible at the time. So this is assuming that you can induce a bit flip after 100,000 hammers. Now, if that number goes down to 100, that probability needs to increase significantly. And as a result, the overheads of the solution in terms of performance and power grows. So that's why the solution doesn't work very well today, at least alone by itself. Okay, so you could do this in the DRAM chip memory controller. I will go through this relatively quickly. And actually, Intel introduced a memory controller where they did this, not exactly in the way we envisioned, but you could change the BIOS and you could pick your RowHammer solution, hardware RowHammer protection or 2x refresh. And if you go to hardware RowHammer protection, you could pick your probability. Now, hopefully your probability is not one out of every other activation. That would be very expensive in terms of how many refreshes you induce. But this is different from refreshing the entire memory. You're really refreshing very selectively, right? It's reactive refresh in that sense. Okay, so if you're interested, this paper actually covers a lot of solutions in not a whole lot of detail, but covers this para solution a lot. So this is an example of a slightly intelligent controller, right? This is what I'm going to argue for going into the future. I think we need even more intelligence. Let's see where we get. So one aside, we actually know how to build these intelligent controllers for other types of memories, like hard disks or storage devices like SSDs. We actually did a lot of work on SSDs. This is our FPGA-based infrastructure where we tested flash chips. And these controllers, if you actually manufacture flash memory, most of the bits don't work off the bat. You really need an intelligent memory controller to adjust the voltages, to figure out whether read disturb is happening, to do error correction, etc., to make it work. If you're interested, we actually wrote papers about it. I'm not going to talk about it. But basically what we're arguing is we need something like this for DRAM going into the future because these scaling issues are going to get much worse. But we need to be even more careful because in storage, flash memory is a slow access device. DRAM is a very fast access device. That's one of the reasons why it hasn't been replaced yet. People have proposed lots of memory technologies because of its speed and cost. It hasn't been replaced yet. Okay, so I think before I go into some more story about what has happened in RowHammer, I'd like to outline two major directions. I think these are active areas of research and people are doing research on it. And we need even more research. I don't think we have enough understanding of it. We need to build these infrastructures to understand the effect of aging. We have a paper coming up at HPCA next week that shows that if you actually keep hammering for 68 days, your threshold, the number of activations you need to induce bit flips reduces over time. So aging clearly has an effect, and we don't understand. 68 days is not long. If a chip is out there for 10 years in space, then the question is it more vulnerable to RowHammer, right? We don't know, basically. So there are a bunch of other effects like environmental conditions, memory access patterns, memory controller decisions, etc., that we need to examine. And then the solution direction is also important, and I think these feed each other. We need more flexible and efficient solutions. I'm going to talk about that a little bit more. And I think co-architecting and system and memory will be important. I think they're in industry. I'm going to talk about industry solutions a little bit. In industry, the tendency is that, oh, DRAM manufacturers should solve the problem, and hopefully nobody worries about it. I don't think that's going to work very well going into the future. We need to have a more holistic solution to the problem. Okay. Any questions? I'll go through some of these relatively quickly because we don't have a lot of time, but I'd be happy to talk about it separately. So what has happened? Intel put the solution out, and you could actually configure your memory controller. And at some point, DRAM manufacturers said, we solved the problem. And then everybody trusted them. So basically, they said, we have DRAM that's not vulnerable anymore. So Intel actually pulled back those solutions. they didn't put them in the memory, or they disabled them in the memory controller at least. So we questioned that at multiple levels. We wanted to understand what is the reliability of chips at a fundamental level, at a device level? I'm going to present those first, and then I'm going to talk about the solutions. So this is a paper that we published in ISCA 2020, 6 years after the original RowHammer paper, where we essentially show that newer DRAM chips are much more vulnerable. We did a larger scale study. We tested more than 1,500 chips from different generations, different types of interfaces. And we saw, for example, in LPDDR chips, you get Bitflips after 4,800 hammers. This is double-sided hammering, so it's really 9,600 activations. And this is 2020. Now today we're in 2024. I believe that number is down. We don't know how much because we need to do those studies again. And these are not, I mean, you could do these studies actually with your FPGA, with the FPGA-based infrastructures. So we also show that existing mitigation mechanisms are not going to be effective if this scaling trend continues. So if you actually get a RowHammer Bitflip after 100 activations, none of these mechanisms are going to be good enough in terms of performance. And actually, once you get into a regime of Bitflips after 100 activations, real programs, benign programs, can become attackers in terms of inducing Bitflips, not attackers in terms of taking over the system, of course, right? But they could induce Bitflips. There are legitimate programs out there that actually do 400 activations to a row because they don't have very good cache locality, for example, or they do non-cacheable accesses for some reason, right? So it's good to think about that. Okay, so I'm not going to bore you with all of these details since we don't have a lot of time. I should probably look at the time also. Okay, 13 minutes. So I'm going to go through it now. I'm going to speed up even more. But basically, these are real data from 1,500 chips, and newer technology generations are much, much more vulnerable. You get Bitflips happening earlier at lower hammer counts, and you get even higher Bitflip rates. Okay, you can look at the paper. And this is the scaling study that we did for mitigations. Basically, this is the number of hammers you needed to induce a Bitflip. From DDR3, you were at this point. And then we're marching to the LPDDR4. This is 4,800 activations, essentially. Now, if you keep marching towards over here, what would be the performance overhead? Higher is better over here. Lower is basically more overhead. You can see the solution. Increasing the refresh rate is a terrible solution, as you can see. Even para is not a good solution once you get into even, say, 1,000 hammer count. So ideal solution, actually, it's one ideal solution over here. Even that loses performance once you get to 100 hammer count. So we basically said we need better solutions to this problem. Okay, so I'm going to skip some of these, but since there was a question earlier, actually there are a lot of interesting things to examine here. Temperature, like physical location of the victim DRAM cell. There's a lot of spatial variation, but I'm not going to talk about that since we don't have a lot of time. Sorry about that. Then there's more RowHammer analysis that needs to be done. We keep developing our infrastructure to look at word line voltage, for example. There's no silver bullet. Basically, you may say, oh, I'm going to reduce the word line voltage and RowHammer is going to get better. Yes, that's true, but it doesn't solve the problem completely. And it caused some other headaches because that messes up with your latency and retention time at that point. Okay, HBM chips are vulnerable, and we have a paper online. You can take a look at that. Let me talk about solutions over here. So we also questioned basically, DRAM manufacturers said, oh, we have this magic solution that fixes the problem. So what is this magic solution? We basically wanted to question this. And this is the work that showed that the solutions are poor, basically. I think this is in general a poor solution for security, right? If you don't want people to access this part of the road, you don't build a solution that looks like this, hopefully, because someone can easily bypass it. Okay, so this trespass work, what the DRAM industry did was they introduced this TRR, which is a very nebulous concept. It's called target row refresh. In the DRAM standard, they basically said, oh, we're going to do some target row refresh to fix RowHammer. And there's very little specification of it. And DRAM manufacturers said, oh, we have this target row refresh mechanism internally that fixes the problem. So what do they do internally? So we did a lot of reverse engineering using our FPGA-based infrastructure to understand what they did. Normally, basically, these mechanisms work by detecting aggressor rows. So there's some detection mechanism in terms of counting, for example. They count the number of different addressor rows using tables. But these tables are of limited size. At least that was our hypothesis. And we wanted to reverse engineer how big these tables are internally in the DRAM chip. And one way of reverse engineering is basically if you keep hammering many rows, maybe you're going to overflow some of these tables and you'll start getting Bitflips at some point. And that's essentially what we did. We introduced this many-sided RowHammer attack using our FPGA-based infrastructure. And we were able to bypass these tables because tables didn't have enough counters. Okay, so that required a lot of reverse engineering, but we have an automatic tool also. So this is an example. If your table is, for example, counting only 2 rows, how many times you access 2 rows? And if you keep hammering 3 rows, the counts are not correct inside the DRAM. So you may actually induce Bitflips. That's a four-sided pattern. And these are data from real chips. For example, after 9-sided hammering, you get Bitflips on this particular chip over here. And in the paper, basically, we report more. In some cases, you need 19-sided patterns to get the best Bitflips, for example. So that's the idea internally. And we actually worked with security folks to do these attacks on real phones. And you can see that we could replicate these attacks on real phones on DRAM chips that are advertised to be not vulnerable to RowHammer. And we could replicate many different types of attacks also. Okay, so basically, these papers together show that RowHammer is an open problem. And security by obscurity, which is essentially the solution direction that has been that the industry has been going towards, is not a good solution. This is still not too well mitigated, I would say. I'm going to talk about more recent solutions soon, but I think we need to be more open in the design of memory and in the design of solutions going forward. Okay, so these two works actually cause a lot of churn. And JEDEC, which is the major body that determines DRAM or memory standards, got together and reformed the task group for RowHammer. They have these white papers. You can take a look at it. I think there's more, from what I hear, there's more coming out from JEDEC about RowHammer this year. Let's see how it's going to be. I'm going to skip this, but you can essentially, the takeaway over here is you can essentially reverse engineer everything inside a DRAM chip that's related to RowHammer. And if you want to know how, our micro paper covers it. Sorry. It's fascinating though. So, okay, let me tell you a little bit about the industry. Industry actually did a lot of work, especially these hyperscalers, because they were worried about RowHammer, right? Microsoft published, for example, a paper at ISCA that showed that you could induce RowHammer through coherence traffic using benign programs. Even benign programs do that. Can do that. There's a lot of interesting stories here that I'm not going to talk about because we don't have time. Google published this beautiful paper where they showed that essentially, if you do a lot of activations to this aggressor A, and if you do a little bit activation to this aggressor B, you could actually cause a bit flip in this victim. Now, this is interesting because if you do a lot of activations to this aggressor, your defense mechanism may refresh aggressor B. And your defense mechanism itself can become an attack to this victim C. So we need to be careful how we design our defense mechanisms too, because there are this sort of mechanisms in place. Essentially, this happens because RowHammer is not just affecting immediately adjacent rows, but there's an effect in non-immediately adjacent rows as well. And actually, we showed this effect in our original paper, but we didn't take advantage of it. But Google showed that this is actually an interesting problem. You can read their paper for more detail. I'm going to skip some of these solutions. There are actually a lot of interesting solutions. So we wanted to build a solution, the memory controller purely. It's an interesting solution, but again, it doesn't scale to RowHammer counts of 100. I think when we go to RowHammer counts of 100, 10, 1, if a single activation calls RowHammer, then you need to think very much out of the box. Okay. So let me tell you what industry is doing right now. Finally, in 2023, this is ISSCC, which is the major circuits conference. SK Hynix publicly wrote a paper about RowHammer, and they talked about some of their solutions essentially. So basically, they're building intelligent controllers inside the DRAM chip. With every row, they have an access counter. And they do some preventive action if this access counter goes beyond some threshold. They don't exactly talk about what they do, when they do it, how they do it, etc. So there's still some obscurity going on internally. And I believe, even though this is a step in the philosophical right direction, meaning that you have some intelligent controller sitting in DRAM trying to protect it, I don't believe this solution by itself is complete, and it has a lot of overhead clearly, etc. But it's a good step in the right direction. At least the industry is talking about it. Now, Samsung, seeing SK Hynix's paper, they had to write some paper also, and they put it on archive. Very hard to read, but there you can get some insights internally. There are other people developing solutions, as I said. Microsoft actually has a solution that's a precursor to Hynix's solution, which has access counters in every row. And it actually has some other mechanisms, because if DRAM is internally not able to refresh the victimized rows, if you will, it basically can tell the memory control, stop, please. I'm doing some refresh. So you can take a look at that. I think this is actually a solution in the right direction also, but I'm not sure if, so one of the issues I think with these solutions, you can potentially prevent bit flips. Two questions. Do they actually work under all conditions, all temperatures? What about aging? If they actually have a threshold that's set that says, okay, access counter is greater than the threshold, I'm going to refresh adjacent rows. How many adjacent rows do you refresh? What if that threshold changes over time, 5 years down the road, right? I believe these solutions are rigid. You really need more more intelligent controllers like online testing based controllers, etc. But these are steps in the right direction. At least the industry is actually talking about the problem seriously. Okay, how much time do we have?
5 minutes.
5 minutes, okay. I can take questions or talk about why we're doomed even worse. Questions or? Okay, maybe I'll go. You can stop me. I can take questions afterwards also. We have meetings, I think. So basically, we're not RowHammer free, and we need to discover other effects. And this is what we did in ISCA 2023 last year. We introduced this RowPress phenomenon. This is actually a very interesting phenomenon. I'll go through this relatively quickly again because we don't have time. Essentially, it's a new disturbance phenomenon. It's different from RowHammer. And user-level programs can exploit it on RowHammer protected chips. And we provide some solutions. So what is it? Basically, the idea is very simple. You activate the DRAM row, keep it open for a long time. Don't even activate some other thing. You'll get a bitflip if you keep it active for a long time. These bitflips normally do not require many row activations. Only one activation is enough, as I said, in some cases, although that requires keeping the row open for 30 milliseconds, which is not legal in existing DRAM chips. So why is this different? Basically, if you have a read disturb phenomenon that doesn't rely on a high row activation count, again, and if your solution is configured to detect the high row activation count, you may bypass that solution. Right? So this is an example. A regular RowHammer attack normally activates an aggressor row very frequently. So you need 47K activations, for example, in this particular case. RowPress keep the row open for a long time. And the memory controller may do this to exploit the locality in the row buffer. And you need only 5,000 activations in this particular example. So we actually built, upgrade our infrastructure to test chips. You can find more information in the paper. Let me give you some real results from chips. So if you do RowHammer, this is activation count you need to induce bitflips. This is across many chips over here. That's why it's a distribution. If you keep the row active, row open for 7.8 microseconds, which is actually valid, legal. 70.2 microseconds is also legal. You reduce the activation count by 2 orders of magnitude, around 2 orders of magnitude. And in extreme cases, which are not legal, only one activation is enough. This gets worse as temperature increases, which is different from RowHammer. RowHammer actually has a very interesting relationship with temperature. We don't quite understand it. Every cell has a different behavior in terms of temperature, whereas RowPress is very consistent. As temperature increases, RowPress gets worse. Okay, I'm going to skip this, and different cells are vulnerable over here. So we showed that on a real system, a real memory controller, Intel Comet Lake, you can actually force the memory controller to keep the row open by activating more, by accessing more cache lines on the same row. And this way, you could induce bitflips in a program on this system where RowHammer cannot induce bitflips. And we actually have more effective versions of this on archive. If you're interested, you can take a look at it. You can run it. All of this is artifact evaluated, and you can actually contact us if you are interested in doing work in this area. So how do you mitigate this? So mitigations, there could be other mitigations, but one of the mitigations that we propose over here is don't keep the row open for a long time. Now, if you keep the row open very little, you're not exploiting the row buffer locality that exists in their DRAM row buffer. So you should keep the row open a little bit. That's what we determine as TMRO. So you exploit some row buffer locality, but now your vulnerability increases. So figure out what your vulnerability increases and configure your RowHammer solution to take that into account. Basically, activate your RowHammer solution more often. And this clearly causes more performance overhead, and it depends on what you're running in the end. So unfortunately, we have this trade-off of complexity, cost, and performance in solutions. And I don't know where to go with this trade-off, but we need more ingenuity, I think, to figure out better solutions. Okay, so I believe there's more to come. I think this is not the end. So there's more effects that we're going to discover in the end. So I think since we're at the end, I'm just going to skip some of these. There's more RowHammer works coming up at this year. These are the ones that I could find there. I believe there are more actually coming up. And there are sessions titled RowHammer, which is good. Let me talk about future a couple of minutes, if it's okay. So future, I think, is not so great. Basically, we're going to discover more of these issues. It's going to consume more of our time. And if we keep iterating like this, industry acts slowly, etc., I believe it's not going to be good. I think we need to rethink the DRAM interface. We need to think about how we can solve these problems without taking a long time. So for example, RowHammer took at least 10 years to solve, and it's not even solved yet, right? We're still discussing how to solve it. But if there was a better interface between DRAM and memory, if the DRAM was more independent, for example, internally, memory manufacturers actually could solve these problems more easily, but they could also be more open about it. So there's actually some trade-off over here. So we could say other memories could be solutions. Unfortunately, all of the other memories, as they scale to smaller technology node sizes, have this sort of problem. Some of them actually have even more problems, like phase change memory is an endurance problem, right? And you need to have an intelligent controller off the bat to handle the endurance problem. I don't have all of the answers, but I think we need to understand more. That's what we're trying to do with our infrastructures. If we understand more, hopefully we can do better modeling and better prediction. And I think we need to architect more carefully, as I mentioned. I think we really need to have patchability in the field. And we need to design and test online, in my opinion. So these issues may not be detected easily while you manufacture, right? Because you may not even know what you're looking for. But online, if you actually do online testing while the chips are in the field, I believe you can actually solve these problems if you actually have the patchability and the architectural mechanisms to actually solve these problems online. So these all go together, in my opinion. Okay. So I'm almost at the end, sorry. So we started with bridges. So human beings have been building bridges for thousands of years, right? And you would think we would be good at it. And I think we're pretty good at it, but unfortunately, these Bitflips keep happening on bridges, right? You may have seen some of these. This is Minneapolis. This is close to my heart. This is Pittsburgh, a bridge that I used to drive on. You could argue there may be different reasons why this Bitflip happened, but it happens, basically. We cannot avoid them. Now, I think in computing, we're in a better space. In bridges, if you want to avoid those problems, if you want patchability in bridges, the cost increase and it's very expensive. But in computing, I don't think it's that expensive, frankly. We know how to do patchability more easily in hardware. In fact, FPGAs are all about patchability in the end, right? Okay, so we need intelligent memories. Maybe I'll talk about this because I have to. So how many people know about this paper? I think Chris knows probably, I bet. Yeah, this is a beautiful paper. This was before RowHammer. It's IEEE Security and Privacy 2003. These folks basically showed that by doing physical fault injection, meaning putting a lamp next to memory and inducing errors, they could take over a virtual machine. I actually read this paper a lot before I worked on RowHammer, and I found it fascinating. But you know, it didn't really excite the security community as much, if you will, because nobody's going to go and go around and put lamps on your machines, right? Maybe in card readers, etc. It would be very interesting, though. Now, what RowHammer did, in my opinion, was simply replace that lamp with software. You could induce that RowHammer much more precisely with software, essentially, because if you actually put that lamp next to your computer, you'll get lots of memory errors. With RowHammer, it's much more precise. Okay, so I'm going to skip this retrospective. I'm going to conclude with one slide, but essentially, memory reliability is reducing. I think these issues are going to open up security vulnerabilities, and I believe there's a whole lot more than what we have seen so far. I think RowHammer is one example. RowPress is another example. There's more to come, in my opinion. Bad news, it's getting worse. Good news, I think we're fully aware that hardware is easily fallible, right? Hopefully, we can work on it. We're both developing both attacks and defenses. Hopefully, we can design more principled models, methodologies, and solutions. I think this is where we're lacking a lot because that requires understanding as well as better interfaces. So that actually goes into a lot of industry level issues that I didn't talk a lot about in this talk, but they're actually really interesting things over there. I'm going to acknowledge my research group because they've done all the work. I'm talking about it. Of course, I know a lot about it also, but these are the folks at the trenches doing the really interesting work. So you can read more about them. And you can actually get all of the information. We open source essentially everything that we do, you can find online. So if you want to build on something, you can actually find it. In fact, we recently open sourced RamLater 2.0, which has off the bat, I don't know how many RowHammer solutions, maybe at least 7 or 8 RowHammer solutions. So if you want to deliver a RowHammer solution, you can simulate it more easily. Thank you. I'd be happy to take more questions. Yes, please.
So it's really a simple question, but for the RowPress, is it just that the row is active, or is there other activities that Bitflips caused by activity of the neighbors' rows?
Okay, that's a very good question. In this particular experiment, we did not activate the neighboring rows, but essentially, RowPress itself is the fact that that particular row is active.
So only that one?
Only that one, yes. Yes, exactly. But I think your question is actually very good in the sense that I think there are some other effects if you actually activate more rows together, and that requires more examination. Yes, please.
You talked about aging a lot. I was wondering, in all these solutions, wouldn't they sort of affect and accelerate the aging of the DRAM chips themselves? And have you looked into that at all?
Yeah. So that's a very good question. Basically, I don't know the answer. So this is something we're looking into more carefully now. The studies are not as easy as you can imagine with aging. So I believe it needs to be investigated, essentially. There's a lot to do over here. Only thing I can tell you about is we did some studies, and as DRAM ages in different ways, RowHammer gets worse. We reported, the only public reporting that we do is in HPCA next week. The SWART paper from GRI has data on the 68 of aging, for example. The RowHammer vulnerability increases by 5 to 6%. Yes.
Maybe one more question, one last question.
There's different ways to construct DRAM cells, right?
Yeah.
Is there one particular implementation of DRAM cells that involves like whatever the ones?
Oh, that's a great question. So again, I don't. You're asking a lot of good questions where I don't have the answers to, or I cannot really give the answers to exactly. But basically, yes, there's slight things you can do. But they change the RowHammer vulnerability, let's say, a little. For example, the word line voltage, right? If you change the word line voltage, you have an impact on RowHammer. The effect is about 10% or so. So it's not huge, I would say. Now, if you want to be huge, you can actually put more distance between the cells. Now, unfortunately, there is a huge impact on capacity of the DRAM chip. So that's why manufacturers don't go through that.
Great, let's thank Onur again for. So you're supposed to have access to the strategy, so feel free to sign up for one-on-one or one-on-one months and interact with Onur. Well, thank you very much. And we will move on to another part.
Thank you.